All right, so in this lecture, I'm going to be talking about data streaming. So again, we are covering Microsoft's Azure specifically, and this is going to be talking about how we stream data in Azure and what services are used. So a little bit of context, the Internet of Things. So the Internet of Things is the term that captures the huge increase in web-connected devices. So this means that things like your refrigerator and your car and your watch and things like that become connected to the internet and send data and receive data from the internet. And so capturing all this data, like for example, all of those Coke Freestyle machines, they all send information back to Coke about their usage and about any maintenance, performance problems, things like that. Jet engines do the same thing. So Rolls-Royce makes jet engines, and they get data constantly from their jet engines as they're in flight, so they can do predictive maintenance and spot problems before the engines actually encounter a failure. And so streaming all this data back, analyzing it, and then taking action on it is part of what's being called the Internet of Things. So the Internet of Things has dramatically changed business models in many industries. So one example is Jim Hackett from Ford said it's a mobility company. Their business is computing. He said some time ago that they're a data company rather than just a mobility or transportation company. GE has talked about the same thing. So jet engine manufacturers Rolls-Royce, Pratt & Whitney, and GE no longer generally sell jet engines. They sell power by the hour contracts. So they basically sell what you would consider like jet engines as a service, where they sell you the engine, but they also sell you the services and maintenance to keep those engines running. And they do so by capturing data from them constantly and planning predictive maintenance and managing their parts inventories very well, and things like that. And that's all predicated on capturing data from those engines. GE does the same, or at least is trying to develop that business model for a lot of their products, because the margins on service are much higher than the margins on just selling the base equipment itself, right? And so to have a service contract to maintain a jet engine is a much longer, more stable, and potentially more lucrative revenue stream than just saying, hey, we sell an engine, people buy it, and then we're done, right? And so the Internet of Things has really allowed this business model to take off and take hold, and these companies to operate as data companies more than just manufacturers or whatnot. So profit in this model, in this services model, comes from monitoring and maintenance, encouraging vendors to reduce downtime and service costs. So if your business model is power by the hour, then you're very interested in managing your service costs to reduce them and managing your uptime to increase it. So the more and longer the jet engine is operating, the more money they make, and the more money the airline makes, and the less money that Rolls-Royce or GE have to spend staging parts or even repairing the engine, the more profit they can make on the services contract. So they accomplish that optimization, or increasing that wedge, by instrumenting and monitoring the system, in this case jet engines. So they put sensors in the jet engines that send information back in real time to a control center. So like Rolls-Royce has a control center somewhere in Britain, and they stream data from their jet engines back there and make decisions and have a constant operations center that monitors all of their jet engines across the world. Um, and so problems can be identified before the jet lands, allowing parts and technicians to be readied to reduce downtime. Preventative maintenance can also be optimized in this way. So most 787s generate about 500 gigabytes of data per flight. By 2026, the most modern jet engines are expected to generate about 5 to 8 terabytes of data per flight. And so for reference, my laptop has about 500 gigs of storage space on it. And so every flight would fill up the entire hard drive on my laptop. Collecting and analyzing this data becomes a challenge. And so once you're capturing that much data, effectively using it to model the performance of your engines, to model the maintenance needs of your product. It's very difficult to make sure that you are capturing and utilizing the valuable data because you quickly start swimming in it, right? There's too much data to store and process cost effectively using traditional approaches. So that is where the cloud comes in. So the cloud has made IoT, again, Internet of Things use cases and solutions more accessible for companies. So the key advantages of the cloud, we've already talked about some, but it has geographic distribution. So data centers located near the edge devices can be used to capture and process incoming messages. So basically, since Rolls-Royce has jet engines all across the world, if their operations center is in Britain, it doesn't make sense to stream data from one of their jet engines in China all the way directly back to Britain. And so frequently what they would do is they would have their devices send data to the nearest cloud data center and then do some basic processing there and then send back the relevant information to their operations center rather than just streaming all 500 gigabytes every flight from all their engines to their headquarters. And so this saves them on storage costs and transfer costs. Transfer costs more than anything, and allows them to kind of optimize their infrastructure and spot problems very quickly, right? Because there could be quite a bit of latency from some of the places their engines are used. And then, of course, increased redundancy, so messages are constantly flowing in, and it can be difficult to retrieve lost messages. And so, if your plane is out there, it's flying, and your one data center in Britain goes down, it may be difficult for you to tell that plane, "Hey, I missed it. I didn't get your last piece of information. Could you send it again?" That may not be possible, because planes and like gas turbines and things like that at power plants. Probably have a limited amount of information they can store, and they may not support bidirectional communication. You may not be able to tell them that you didn't get that message, and so it's very important that we have redundant infrastructure to receive these messages. Since in some cases, if we miss them because the internet was out or our server was down, those messages may be lost forever. And we may miss critical data. And so the cloud allows us to be redundant geographically and have more highly available technologies, highly redundant technologies, to minimize how many messages we'll lose or miss due to any kind of unpredicted outages. So it can be very difficult to retrieve messages that were missed because the receiver is down. That's right. So this can be due to bandwidth limitations. We're playing. Oh yes. So why is it difficult to retrieve some of the missed messages? I talked about that a little bit just a minute ago, but it could be one of a couple things. It could be that there are bandwidth limitations. So if we have a field site or something like an oil and gas well in a rural part of New Mexico. We probably do not have a direct connection there, like a fiber optic link or anything like that. It's probably over radio or maybe over cell. And so if we missed quite a bit of data, it's very difficult from a network perspective to get that data back because we're very restricted. We're very limited on how much data can be sent at a time. The internet pipes are very small to some of these locations. The other side is many IoT sensors and devices have very limited memory and storage. So a lot of these processors or devices that are out there capturing the information from these sensors are very small and very lightweight, both from a cost perspective, because if it's an oil and gas company, they have a lot of wells, and it doesn't make sense to spend a whole lot of money on devices to monitor all of your wells, to have very powerful devices monitor them. Usually use much cheaper, more cost-effective devices. It also can be hard to put robust, large devices out in a field location because your power constraints are limited. Sometimes you have to rely on solar or intermittent power, things like that. And so usually the devices that are put out in a lot of these industrial settings are fairly small and fairly lightweight and have limited memory storage and processing, which means they can't store a lot of messages if we have the receiver is down, right? So businesses, finally, obviously, also cannot act on messages they haven't received. And so if we are Rolls-Royce and need to receive information about our jet engines in order to do predictive maintenance, or even to do urgently needed reactive maintenance for an engine that's going to fail soon. Obviously, if we miss the messages from that engine, we cannot schedule the maintenance and notify the airline and things like that, right? So it's very important that we get the messages so that we can actually do something, so that we can actually act on them, right? So IoT devices are also generating more and more data, which is frequently used to train algorithms and discover trends. So IoT devices, so we're putting more and more sensors, like people have watches now that monitor their heart rates, right? That generates quite a bit of data that monitor your activity level, can do things like tell you about your sleep cycle. All of this data generated from wearable technologies is new data that wasn't being captured before for a lot of new people. And so capturing this data and processing it, like what Apple does to predict like heart arrhythmias, the more data we have, generally the better the predictive algorithms that get developed based on that data are. And so if we have data from 5 people and train an algorithm on heart arrhythmia, that algorithm probably will not be as good as if we had data on 5,000 people, which probably won't be as good as if we trained one on 50,000 people. The returns are diminishing. 5 million, an algorithm trained on 5 million people may not be that much better than one trained on 50,000, but one trained on 50,000 would be a lot better than one trained on 5. And so diminishing returns do kick in somewhere, but generally the more data we have to do things like build predictive models, the more accurate those models and any subsequent reporting or analytics would be. And so IoT devices are generating more and more data, and companies want to train algorithms and generate insights based on that data. So they obviously have to store and process that data. So storing and processing these vast quantities of IoT data can be very expensive using historical approaches and on-premise infrastructure. So if I have to store all of the data, if I'm Apple and I have to store all the data from everybody's Apple Watches, it could be pretty expensive to store and process that in my own data center, where I have to buy hard drives. But using cloud storage like S3 is very economical, it's very cheap, and we could use services like Elastic MapReduce and Spark to do bulk processing in the cloud on demand, which makes it very much less expensive to store and to train these algorithms using on-demand compute, on-demand clusters like Elastic MapReduce. So the Internet of Things, it can be thought of in 2 large problems: data collection. How do we get the data from sensors as it comes in, and how do we make it ready for analysis very quickly? And then managing the endpoints or sensors. So if I'm an oil and gas company and I have a bunch of sensors at 20,000 wells spread across multiple states, how do I manage that to make sure no unauthorized sensors are sending data? How do I update the sensor software? And how do I track the information about those sensors or about devices connected to those sensors, right? So I want to get the data, and I also want to manage the things that are sending me data, right? And so those are 2 key challenges that different products in the cloud seek to solve. So the data collection side of that, so streaming data means moving and processing messages or payloads as they are received. And so streaming for data just means I'm processing it as I get it. Usually people would think of that as being real time. So this is described as real time in many cases, but that could be misleading because real time implies little to no latency. But many messages could be minutes or hours old in practice. And so whenever people think of real time, they generally think of as the event is happening, right? If something happens, then I would get that message right away and do something on it. And that's not necessarily what streaming involves, what streaming means. So in this case, streaming just means, hey, as the message is generated, the device is trying to send it. And as I receive it, I process or act on it as I receive it, each one, rather than saying, hey, I have a job or a process that operates on a schedule, which would be batch, as it says here at the bottom of the slide, right? And so if I run a job every night at midnight, that would be a batch process, right? I run it no matter how many messages I got. I don't care when I got the messages. I run a job to generate my revenue by state report every night at 10 o'clock. That's a batch process. It's on a schedule. It doesn't matter when the data came in or how much data I got. I process all of the data every night at a certain time. Streaming is the opposite of that, where streaming means I don't have a schedule. I process every piece of data as soon as I receive it, right? And so that's a data streaming job. But it could take you hours to process that data, depending on the job, or it could take minutes to process that data. It doesn't really matter how long it takes you to do whatever, to apply your algorithm or do your training or something like that. And that's why it can be a little bit misleading to call it real time, because real time generally means instantaneous to people, and processing streaming data is not necessarily that. There can be some latency, some delay involved, just depending on the technologies and the type of work that you're doing on that streaming data. All right, so batch was, for many use cases, sufficient in the past, and it is easier to implement batch. And so it's easier to say, I'm not going to worry about trying to capture data and to write some piece of code or some program that can operate on each piece of that data individually. It's much easier to say, every night I'm going to forget everything I have. I'm going to totally reprocess all of the data that I have. It's much easier to say that, right? To say, all right, every night I'm going to regenerate my state revenue reports, and I'm going to read in all the data, I'm going to process it all, and I'm going to create the report from scratch every night. That logic is much easier to express. The technologies are much easier to use to accomplish something like that than to say every time I get a receipt from every store in every state, I process that and I add it to my report in real time. That tends to be harder to develop, and the technologies tend to be more complex. And so batch processing has been around for a long time, so has streaming. But most companies, data processing work happens as a batch process. So most companies have a lot of batch processes that run overnight to generate the reports that people look at in the morning and then make their decisions. But increasing business agility requires more timely access to data. And so if companies want to have a more real-time reaction to their marketing campaign, or adjust their supply chains to unexpected events, more quickly than the next day, if they want to make near real-time adjustments to things like prices or inventories or things like that, that requires streaming data, right? That requires not doing things in batch, because with batch processing, we generally don't have the answer until the next day. So that's a lag of many hours. And so more businesses are trying to become more agile, which means they're trying to do more real-time data movement and manipulation work. So data streaming has moved to the forefront, and many PaaS services exist to stream and process data. So both of the cloud providers, both Microsoft and Amazon, are trying to provide more services that make it easier to process streaming data. That's basically the so what. So a few of those services. So one of them is a message broker. A message broker exists between devices that produce and publish data and the devices or applications that consume the data. And so a message broker, like we talked about a little bit last week, is an intermediary. So a message broker would exist between the jet engines for Rolls-Royce, where all of the jet engines would send all of the information they captured to a message broker in Azure or in AWS. And that message broker would store up the data, and it would keep a history for several days for all of the engines. And then anybody that wanted to train an algorithm or deploy an algorithm or even just run a report would then hook up their dashboard or their machine learning environment to that message broker and consume the data from it, right? And so what that keeps us from needing to do is connect every jet engine with everybody that wants data from them, right? That'd be very difficult to do, because there would be tens or hundreds of thousands of jet engines that Rolls-Royce has. and who knows how many people interested in receiving that data. And so instead of doing that, dense spider web of connections, all the jet engines talk to one product, one platform, one solution, and then all the people that need that data know where to go, right? They go to that message broker and they know they can get the data from it. So a broker exists to allow one or more devices to send data to a centralized location where one or more applications can consume it. That's right. So message brokers are usually designed to be capable of very high throughputs, capturing tens of thousands of messages or millions of messages or events per second. And so these message brokers are designed for a massive scale and are used as such by companies like LinkedIn and Twitter and Facebook. And so they send messages about what users are doing on their platform or other kinds of analytical metrics to a message broker from all of their websites, all their web servers, and then people can consume them. Machine learning models can consume that data and actually run it and process it and take action based on it. And so message brokers are intended to be very lightweight pieces of technology that are capable of processing a whole lot of data very, very quickly, processing and storing a whole lot of data very quickly. So anyway. The message queues are very similar to a broker but distinct. So message queues are generally used to allow two applications to communicate asynchronously. So a message broker allows a lot of producers, a lot of devices out in the field or web servers or things like that, a lot of systems that are generating data. A message broker allows a lot of those to send data to one place and a lot of people to consume that data from that one place, right? A message queue is more intended for one-to-one communication, right? One application or solution creates data and sends it to a queue, and then another application or solution picks it up off the queue. And so what that allows us to do is instead of the producer sending messages and the other immediately acknowledging and accepting it, right? So if I have two applications, one of which is maybe creating transactions for a customer, and the other is receiving those and updating their balance. If I want to make it so that one can just send an event about a purchase and the other can process that purchase whenever on its own schedule, I would use a queue. And so the queue would store all of the events, all of the transactions, all of the purchases, all of the notifications, and then whatever was actually processing those would pick up the messages off of the queue and process them one at a time in order, and that would allow me to not have to wait, right, for the whole system. So if I wanted people to just make a purchase and then the balance to get updated and reflected later without holding up the completion of that purchase, I could use a queue. And so synchronous means that one application sends a message and the other immediately acknowledges and processes it, right? So the first one has to wait on the second one before it moves on. That's what synchronous means, is they do it together, it's synchronized, and you have to finish the whole thing before either one of them can go on about their business. Asynchronous means that one sends a message and moves on, and the receiver could process that message minutes or days later, right? And so the transaction solution creates the transaction, puts the message on it, puts a message about that on a queue and goes on, and then the processor picks it up whenever, maybe overnight, processes them all, updates everybody's balance, and that would be asynchronous. So a message queue is intended to allow two solutions to talk to each other asynchronously. So it acts as the buffer in the middle, and again, it differs from a broker in that a broker is intended for many-to-many type communication, and a queue is generally one-to-one. So message queues are designed to allow a message to be read once and only once, and so that's why it's a one-to-one. After a message is read from the queue, it is removed, it is destroyed. Brokers are distinct and they don't destroy messages when they're read. Brokers only destroy messages when they're a certain age. So basically, brokers keep messages for usually 7 days on average. And if 1,000 people read that message, or if nobody reads that message, they age out after 7 days. But usually that's configurable. 7 days is just the default. Unlike a message queue, which never ages them out, it keeps a message until somebody reads it. And as soon as somebody reads that message, it's destroyed, and nobody else could retrieve it in general. So brokers work differently because they're designed to allow many-to-many communication. Yep, that's what I already said. If 5 applications want to consume the same data for different purposes, it makes sense to retain it. So if a lot of people are interested in the jet engine data, obviously I don't want to delete it. I want to keep it on the broker so that other applications can come and retrieve or consume that information. An analytics application may only check for new messages hourly. A streaming dashboard may check constantly. Brokers accommodate both of these. So if I'm a data scientist, I may write an algorithm that only looks for suspicious transactions every few hours, or may look for anomalies in supply. If I'm writing an application for a supply chain company, it only may make sense to check my supply levels every few hours. And so a message broker would allow me to do that. I could come back to the broker every 5 hours or however often I wanted, read the messages for the last 5 hours, and update my algorithm or my report. Whereas obviously, if I didn't have the broker, I'd have to try to receive those all the time, right? So Event Hubs is a platform as a service, publish, subscribe message broker. So Event Hubs is a message broker in Azure. Pub/Sub message brokers mediate between producers and consumers. That's what we've already been talking about. We have systems that create data, that create information, and they put it on the broker, and consumers receive those, right? Consumers retrieve the messages. And so a producer sends the messages, a consumer retrieves the messages. All messages are sent to and received from a topic. And topics can have 0 or many producers and 0 or many consumers. And so, so for Rolls-Royce, they may have a topic for engines, and they may have a topic if they receive information from cars, and they may have a topic for all their other product lines, right? And so a topic is kind of what the name implies. We would put similar kinds of data on a topic, and we would have one topic for each data type. And it's just to keep it separate, right? Because a report or algorithm that's interested in jet engine information is probably doesn't want to receive information about car engines, right? They're probably different. The data they generate probably looks different, and so we would have separate topics. And so topics just allow us to separate the data in whatever way makes sense to us. So HTTP and AMQP are different protocols that can be used to send the data. So AMQP is intended for message queuing. So HTTP is the internet protocol. Anytime you go to a web browser, you'll see the http://www. It's just the protocol of the internet, the hypertext transport protocol. And so that basically just means, hey, I can talk to an event hub like I would a website, right? And I can just send it messages in the standard language that we use to connect to the internet, which makes it very generalizable, right? Almost everything knows how to talk HTTP if it knows how to connect to the internet, because again, that's really just the language, the machine language of the internet. AMQP is slightly different. It's a specialized protocol that's designed for message queuing, designed to be lightweight, specially purpose-built for sending messages, IoT messages, to a message broker or message queue. Unlike HTTP, which was really built to run the internet, right? So AMQP is specialized, and as such, it's more efficient. HTTP is general, and it's obviously less efficient because it tries to do a whole lot of things, right? And so I have all these producers that are generating all this data, right? So each of these data streams could be a different engine, or it could be a different register in my stores, and they send the data using one of these languages, HTTP or AMQP, to an Azure Event Hub, which is my publish subscribe message broker. And then within Event Hub, I have multiple partitions, and these partitions help me with throughput. And so more partitions allows me to receive more messages more quickly. So each partition is kind of like a thread, or it's like a different compute, like a CPU almost, right? Where if I have a bunch of them working together, I can receive a whole lot more data, right? So if I have one partition, I cannot receive as much data at a time as if I have 4, and 4 can't receive as much as if I have 16, right? So more partitions just allows more throughput for this message broker. And then I have groups of consumers which have to read from each of these partitions to get all the data. So some of the data goes on 1, 2, 3, and 4. And so when a consumer comes out here, it has to receive data. It has to retrieve data from each of the partitions to get a full set of all of the data, right? So topics are types of message streams that are types of message streams are broken into topics, which are further broken into partitions. And so again, I already talked a little bit about topics, but topics are just the type of data, right? And so I have data about engines or cars or cash registers. Each of those would probably be a different topic because different people will be interested in different ones, right? Almost nobody's interested in all 3 of those in the same data stream or report. So topics are generally created for different types of data. Drilling versus completions in oil and gas would be 2 different topics because you get different kinds of data from a drilling rig than you do a completions crew. Could also be geographic or business segments. So yeah, so sometimes we would create different topics for different business units because they're not interested in each other's data. So like our Rockies business unit may have a topic and our Delaware business unit may have a different topic because again, they'd want to provide different reports and maybe even run different analytics if their business challenges are significantly different enough, right? So partitions are really shards within a topic. They exist so load can be distributed. So that's what I talked about. More shards or more partitions mean the topic can handle more messages at a time. So they just increase the messages throughput, right? And so more partitions means I can handle more data per second, and fewer means fewer. In event hubs, an event hub is analogous to a topic, and so we'll see that. But basically, we create an event hub. Namespace is what it's called, and then we can create multiple hubs within that, and each hub is basically a topic. So I can have many event hubs in one namespace, and that namespace is really just a container. It's just a bucket, right? And so similar to making an S3 bucket and then folders within it for the different data types, I create one event hub's namespace, which is like my container, and then I create a bunch of hubs inside of it, which are like my folders, and then I would organize my data within those folders, right? And so I can have many partitions in an event hub. Producers send data to one event hub, and consumers subscribe to one event hub. So you basically, I said event hubs are like topics, right? You send data to a topic, whatever topic's the most relevant, and you consume data for a topic, and again, whatever topic's the most relevant for what you're trying to do. And so again, with partitions, so messages in each partition are stored in the order they're received. So I have newer messages. It's basically a first in queue, right? And so the older messages are on the left, and then each newer message just gets appended or added to the end of it. And then over time, the older ones are aged out, right? And so if I keep them for 7 days, once those older ones become 7 days, they start to fall off the left side, and newer ones keep getting added on the right side. So messages in each partition are stored in the order they're received from the oldest to newest. So if something like a sensor value changed 5 times in the last day, all 5 of these records are kept. So we don't go in and reconcile or duplicate them. And so this partition is like a full change log. It has all the information that happened for the sensors, for the registers, all the transactions. And so if we sold a corn dog at a store, it would send that sale to the partition. And then if that corn dog was refunded or canceled or somehow otherwise reversed, we'd have another message for the reversal, right? And so then we'd have 2 messages, and we need to look at both of those and process them to know how much we sold, right? Because all we're doing is capturing the data and appending to this partition with the newer data, right? And so it's not like a database where if we update a record in a database, there's still one record and we just change the same one, right? All we're doing here is appending new readings or new information to the end all the time. And so any consumer has to go in and say, okay, I said if you were going newer to older, you'd say, all right, I see I reversed a corn dog sale. keep looking back. I see I made that corn dog sale. Okay, these two cancel each other out, right? And so you would process the data, and you could process it in the order it was received or backwards, and reconcile all of your transactions and charges and things like that using the partition. All right, finally, so that's what makes partitions similar to what are called commit logs. So commit logs in a database are a history of all the activity that has happened, and they don't try to consolidate it or make sense of it. So it's exactly what I was saying. So we just constantly add data to the end of it, and it makes it extremely fast to write to and read from a message broker, because it's not looking to say, do I have a record for this sale that I'm reversing? Yes, I do. Let me update that one. It's just saying, all right, I reversed a sale. All right, I made another sale. I made another sale, right? And so it's just constantly just trying to capture the data as it comes in. It's not trying to make sense of it. It's not trying to process it, reconcile it, or rationalize it. It's simply trying to capture all the data that's being sent to it. So it does mean consuming systems. So anybody building a report or an application that consumes from this system have to have their own logic for merging events. So they have to have their own logic for looking and tabulating the sales or reconciling the figures, for the airline sensor or something like that, right? And so it means the data is fairly raw. That's really what that boils down to, right? The data is in a very raw state as it was sent and as it was captured from my devices, right? And so there, I'm gonna pause, and I'll pick it up in the next video.